Okay. All right, so we're going to move today. You know, let's pack in 2 hours in 1 hour. So I've got a Markov chain, which we described last time. It's a stochastic process on some state space X. And when to keep that abstract, it'll be like Rn, or maybe the integers like we saw last time for that random walk, something like that. And that's an example of the Markov property. Well, that's the Markov property. So I said it in terms of probabilities, but you can also say it in terms of functions. So this is a bit more general. Say, just to make sure everything is meaningful, for every bounded and measurable function from the state space to the real numbers, if I take the conditional expectation of a function one step in the future, given the past, the last state is a sufficient statistic. You know, that's the definition of a sufficient statistic. You know, that xn is sufficient to predict the future. I don't need anything more. All right. So that's the Markov property. That's another way of saying it in terms of functions instead of probabilities. And this is the time homogeneity property. That if I look at the conditional acceptation one step in the future, that doesn't depend on what time I'm looking at that. So if I put, and this is true for any n. All right. Yes? Okay, so then what's this? So I'll put a definition here. So I've got an n there. That came up without much justification towards the end of a lecture last time. No, it was in the middle of lecture last time. My definition, which I will justify, is what? H, I heard an H, good. There's an H there, so we're going to repeat that. And? No T's here. Oh, T plus N, all right, cool. Yeah, oh, I love it. Oh man, thank you. So we don't have to have the exam today. All right, cool. But I'm going to make you write this. I'm going to give you a homework assignment where you're going to have to just write this down 100 times. I swear to God. Because if you don't accept that notation, I can't do anything. And we're going to use this actually, you know, the Markov part's only going to be maybe a couple of weeks. But then we're going to go to hidden Markov models. And we're going to, you know, talk about all sorts of applications in Markov domains. And if you're going to make me write this out every single time, I can't do anything. I'm stuck. You know? So you just got to memorize this. All right? All right. So let's justify, why would I use this notation? It looks like I'm looking at a product of matrices. Well, that's because that's what it is, as we shall see. So, you know, previously I really only defined. Yes. Okay. So I made a bit of a mistake last lecture because I really wanted to give you just a quick, cool application of performance bounds for Markov chains, and I forgot that I needed one more step to explain where I define this thing. And let's explain the notation. So let's just consider what is the expectation of h of x t plus 2 given xt equals x. You know, so I'm not asking you to say that. I mean, let's go think about this. So we can use the Tower property or the smoothing property. I had never heard of the tower property until I came to Florida, but it seems to be, you know, the lingua franca here. I've always called this a smoothing property, okay? But so basically, you can take a conditional expectation with respect to a larger sigma algebra. So here we're taking the conditional expectation with the sigma algebra generated by xt and xt plus 1, and then, you know, take the conditional expectation with respect to xt. Now, we've only defined conditional expectations like that, you know. We all know a conditional expectation is a function of the data. So I'm just saying that function at x, it's a shorthand for that. All right, but now you use the Markov property, all right? So, you know, I mean, it's a bit of a waste of ink, but let's do it. All right, is that clear enough? So I've kept the x equals x, and I've just gone through and I've eliminated the xt because of the Markov property. So that's the Markov property. That's crucial. And then what's this? Don't maybe give the exam now. P, pH, pH, pH. That's pH evaluated a random quantity. So I take H, I hit it by P, and then I stick in a random quantity. But that's too confusing, so I'll just give it a name. A new function here. You know, it's very confusing to stick the p's in there. So p was a mapping from functions to functions. It's defined, it's deleted now as a conditional distribution, conditional expectation. So p is a mapping from functions to functions. But you can see why it's really important to make this thing. If I had the p there still, it would be too confusing. Now I can say, damn it, this is what I said you better memorize, I'm going to kill you. What is this? pH1. All right. So I'm taking H1 hitting by P. Anybody call that P squared? It's P hitting PH. You know, so it's all right, so that's the justification for the notation. So somebody challenged me last time about all this, and that's it. All right, cool. So let's now specialize to something more concrete. Let's look at a finite state space Markov chain, and think about kind of the way people think about this in an undergraduate course. But I'm going to pretend you're all control theorists. I mean, basically, forget that. I'm going to pretend that you know that you're comfortable with matrices. I know half of you aren't, but I don't care. You've got to become comfortable with matrices. It's about time. And eigenvalues, and eigenvectors, and Jordan canonical form. I think Jordan is the biggest evil that ever happened. Life would be so much nicer without his canonical form, but we're stuck with it. I don't know if anybody was here when I was screaming that mathematics is overregulated. We should have more axioms. We should be able to make up our own axioms. Then we could get rid of the Jordan canonical form. We could say every matrix is diagonalizable. We do it by decree. It'd be beautiful. You know, it's what a wonderful world. Okay, so I could say that. I could say in this course, every matrix is diagonalizable. Jordan was wrong. He should be in jail. And he's French anyway. But we're stuck with that. So math is overregulated, and we're stuck with that. So we've got a finite state space Markov chain. And we might as well just take x to be just integers. So Okay, I mean just label them 1 through n. All right, and then we have typically people immediately now draw a state transition diagram. They'll write a 1 here and a 2 here and a 3 here and a 4 here and so forth, and you end up with a directed graph. So here's n equals 5. So this is the way, when you go through an undergraduate course in probability and everyone falls asleep at this stage, you write down a directed graph, and the 2 errors going to 2 is a bit weird. All right, and there are weights on these edges. So this is obviously the probability of going from 1 to 2. Etc. All right, and then they go around and talk about graph theory and connectedness and all right, forget all that. I mean, it's useful. I mean, basically that sort of computer science view of probability or undergraduate is useful, but there's it doesn't. I mean, it gives you some insight, but not but not enough. All right. So this is sort of a usual way of thinking about it. Let's forget all that and go back to my favorite operator P. So if I take an expectation of h of x t plus 1 given x t equals x, we know x is equal to 1 to, or in. X is just a number between 1 and n. Well, we all know that's equal to the summation k equals 1 to n of the probability that x t plus 1 equals k given x t equals x, and then times x h of k. I wish I'd run out of room. You would all agree with that. That's how you take a expectation, all right? When you take basically to compute a conditional mean, you can do it by having the conditional distribution. So now we're going back to the very basics. I mean, what I've avoided talking about, because I want to think of conditional expectations as an LP2 projection. Another point of view is to compute the conditional distribution and just sum. Right? Now, if that doesn't look like matrix vector multiplication, there's something wrong with you. I mean, really. I mean, that you really need to refresh on matrices. All right. So why do people never accept this notation? If taking a conditional expectation turns into a matrix vector product, why would that be so hard to accept? So at the end of the semester, I want one of you to explain to me why I've never gotten the students to accept this notation. It's P times H. So tell me, maybe anybody tell me now? Why does it frustrate people so much? They get so lost. Why? I mean, Jesus, isn't that, if this is an n by n matrix, that's how you'd multiply a matrix into a vector. The hard thing is you have to think of functions as vectors. Big deal.
So H of k is an n by 1 vector?
Yeah, H is a vector that's, it's a column vector that's size n. Big deal. But this is what gets everyone stuck, and then we don't get anywhere because people won't accept the notation. So anyway, I'm really curious. It's just something that fascinates me. It was true at Illinois too. So this is where I got stuck. So I don't want you to get stuck. I've never tried this hard. I want to somehow get past this slush, and you all to agree that you accept this notation. All right, so let's play with it. So we also know that we could do this again, like I said before. We have it over there. You know, we have this, if we did this twice. So I'm just rewriting what I had before, right? You know, I've got the H1 equals pH. I'm just recopying this in the finite state space setting, and I've just told you what that is. You know, so I've got H1 is taking H thought of as a column vector and hitting it by matrix P. And now I'm doing is I'm taking H1 and I'm hitting it by P again. We'd all agree that that's P squared times H. It's matrix multiplication. I mean, you can expand it out if you like. So if you sum over z, you know, we're summing over two variables. I took a sum outside, I cheated. But the H1 was the sum over z here. No, it was sum over y. I cheated a lot, I took the sum over y way outside. Or something. I cheated somewhere.
That's a question.
Anyway, it's a double sum. It's matrix multiplication. Yes.
The first argument to the P matrix, is that the x at xt plus 1 or the x we're given?
No, is this a matrix?
No.
Well,
Is
no.
it the x we're given, or is it the probability of
No, it's right here.
So
It's right here. It's right there.
it's
It's
the x we're given.
No, but you tell me. Yeah. Now don't ask the question, figure it out. I wrote down this to this. I don't want to answer, I want you to tell me.
That's the only confusion.
No, take a look at an X and a K, an X and a K. Right? Yeah, so you know the answer. You can look at it right there. X, K. Yeah. So I've got the probability of going from X to K. And that's the probability of going from, yeah. Right, so you know the answer, it's right there. And so, yeah, so basically the way you read it is the probability of making a transition. Just like over here, the probability of making a transition from 1 to 2. Okay. Yep.
Here, P is an n by n matrix,
Yeah.
but I guess maybe so the other day Tuesday we were discussing the transition matrix from X to some set.
Yeah, and now in a finite state space setting, the sets, we just look at primitive sets, singletons. Yeah, we don't have to worry about that anymore, yeah. Yeah. Okay, so anyway, so basically, this really is, in the finite state space case, we're just looking at products of matrices. So, so remember last time I was talking about, like, I want to look at the mean of something in the future. Let's stick to H since we started with H. I'm interested in things like I'll call it H, say n of x, which is this Pn, Pn H evaluated at x. So again, I'm always taking H, hitting it by this matrix power, and then evaluating. Right? And this, of course, is equal to p to the n minus 1 times h n minus 1. I'm sorry, p. Just from the same sort of things that I've been talking about, right? I mean, we all know, after all, we have this fundamental identity. The fundamental theorem of matrix multiplication. All right? So once you define Hn to be p to the n times h, we clearly have this identity, right? All right. So, and again, it's a linear state space model. It's the most boring linear state space model you can imagine. There's no input. It's discrete time. It's completely fall asleep boring linear system. You know? Now I told you before that Markov chains were state space models like this. One second, just wait. I told you the Markov chain itself is a nonlinear state space model driven by IID noise, right? But this is nonlinear and noisy. When I look at these conditional expectations, I get a linear state space model, you know? So this is some horrible mess, but the distributions are evolving linear in some way, the conditional expectations. And that's one of the things that makes this theory of Markov chains so elegant, is you get this, you can apply linear intuition, you know. So think of H, it's like I said, it's like a column vector. I've got the evolution of this state vector, if you like. Just think of it like that. It's just if you've taken a control course, you look at models like this. Usually there's an input as well. And also, you can kind of imagine products of matrices shouldn't be too hard to think about. So now, you had a question?
Going from the top line to the second line, how'd the power switch from P to H?
What? No, I have a definition.
Pn times H to P.
This is true for any n.
Times P to the H to the n minus 1.
This is true for any n. It's true for n minus 1 too. I mean, P to the n minus 1, H is what I'm calling Hn minus 1. This is just a definition, not a power. This is just a definition. I'm making a definition. So I'm taking a function h. This is the definition. For any n, not just one n. And I said I'm joking about the fundamental theorem of matrix multiplication. Let's do it then. So I'm defining Hn to be p to the n h. And that's p times p to the n minus 1 h. That's all.
Okay, yeah.
So I'm just grouping things.
Can you define that to be H to the n minus
Well, it's true for any n. It's any n. It's notation. Any n. I'm not redefining anything. I said this is true for any n. And so that, of course, is Hn minus 1. Right, yeah. Okay, cool. So does anybody know anything about state space models? I mean, they can be unstable. All right? This could blow up. Anybody think it's going to blow up? Take a look. So is that going to blow up? Is that going to, if you take a control course, you think, my God, this could blow up geometrically quickly. Is that going to blow up geometrically quickly? H is on a finite set. It's like less than its maximum. It's a stable system in that sense. It's not going to blow up. All right? So it's a very special state space model. And in particular, given the fact it's stable, its eigenvalues must have some special properties. So if you're a control geek like me and you see a state space model like that, you say, oh goody, I get to play around with eigenvalues. And so you draw the unit disk, and you know that the eigenvalues must be within the unit disk. All right? Now, it could be marginally stable. I'm not saying this goes to 0, but it doesn't blow up. All right? So I know that there's something like this. Now, I claim there's an eigenvalue at 1. Why do I think that? Anybody can think of an eigenvector for P? Anybody see an eigenvector? Given this, yeah, take a constant. I'll take all ones. So if H is a constant, the expectation of a constant is that constant. So we always have a right eigenvalue, which is 1. There might be multiple, so there's an eigenvalue there, I'll call it lambda, say 1 equals 1. It could be repeated, and that has consequences to the graph that I just deleted, which we'll come back to in a second. All right? And all the rest are inside. And maybe there's some on the imaginary axis as well, because that doesn't rule out things blowing up. On the bike ride over here, I thought, what? I've never in my life thought of this until this morning, or this afternoon. What would happen if there's multiple, complex eigenvalues? That sounds crazy. I don't think I've ever heard anyone ask that question. I know I can give you examples where it's true. You could have repeated eigenvalues. Now that's dangerous, right? If you know about Jordan canonical form, when you have repeated eigenvalues on the unit disk, that's instability. I mean, you can, potentially. You get these Jordan blocks and you get polynomial explosion. But it can't happen. So there must be some very, very special structure when you have repeated complex eigenvalues on the disk. Okay? But what happens? What if we had? What happens with other eigenvalues? So suppose we have another one. And okay, I'll call it V just for your benefit. Because that's what we usually call them when we're talking about matrices, right? And so we've got PV equals lambda V. All right, and V is a column vector. But column vectors are functions, all right? So I'm saying here is the expectation of V at xk plus 1 given xk, well, given xk is at lambda times V of xk, right? PV is considered expectation, all right? And, V of xk, V of xk. Yeah? If you accepted that, you got to accept that. You're stuck now. Right? And I could say the same thing. I know P to the n V is equal to lambda to the n V. I can iterate this equation. I can hit it by P over and over again. And so I get the conditional expectation of V of x k given x0, say. So just, so I've got that for all k. And then ends. So I've also, when I iterate the eigenvalue equation, I hit the left hand by P, I hit it over and over again, n times I get this equation. And so I get that this is equal to lambda to the n V of x. And what's going to happen? Well, lambda's in here somewhere. And if lambda equals 1, this is just constant. And we saw an example of that. V equals 1 is an example. But imagine if we have a complex eigenvalue. If we have a complex eigenvalue, right on the imaginary axis, So if we have a complex eigenvalue, so right on the unit circle, so its magnitude is 1, but it's not equal to 1. So it's one of our friends here and here. All right. Then this thing is spiraling around. Lambda to the n is just going around. You take power as you spin around the unit circle. And so basically the expectation of it doesn't converge, it just does stuff like this. So like if this is a problem where we're trying to evaluate the cost, trying to predict the cost in the future, well, our prediction is it's spiraling around. It'd be a very weird system, you know? Yeah, so it wouldn't settle down. We could take the average and that would be okay. So if we average both sides, we'd get something reasonable, but that's all we could say. All right, V is complex. I mean, if lambda is complex, so is V. But I mean, if you had a Markov chain like this, you could predict that you'd get some spiraling behavior with more general functions, not just eigenvectors. I mean, you know, that's how these things work. I mean, you know, okay, cool. And then, of course, if we're strictly within the unit circle, then things go to 0 geometrically fast. Okay. Okay, so I'm going to give you a definition which is completely wacky. The word is standard, but my definition is completely not. A unit chain good. Behold, so this is the imaginary axis, and this is the real axis. So the unit chain case is where I've got all the eigenvalues are strictly within the unit disk, except for 1. We know there has to be 1 at 1, and that's not repeated. So I'll tell you the standard definition later on, maybe next week. But let's just stick with this and call it a definition for now. So that's not the way you'd see this in a probability course normally. It's a definition tailored for an audience in this signals control communications community. Okay. I mean, this, not the words, but this is a really reasonable assumption to rule out the crazy behavior like this, So what do you do with this? It says that I've got a whole subspace of functions that are going to 0 geometrically fast. If I look at any eigenfunction associated with these eigenvalues, they're going to 0 geometrically fast. And I've just got this one stubborn eigenfunction, which is 1, which refuses to go to 0. And I'm going to show you an algebraic trick. Please, yes. Just like there's a right eigenvalue vector, which is 1, there's a left eigenvector which I'm going to call pi. And pi is not like today's, not pi day. So pi is a row vector. So you can show that this sum is non-zero. I won't do that now. But let's normalize it so it's 1. In fact, it's non-negative. It's a probability measure. Okay, it could be have 0 entries, but it's actually, we'll see it's non-negative. I mean, I just don't have time to prove that right now. But that doesn't